A zero-sequence current transformer, or CT, detects ground faults by measuring the unbalanced current flowing through the three phases when a fault occurs to the ground. Under normal conditions, the sum of the three-phase currents is zero. However, during a ground fault, current flows through the ground path, resulting in an increase in the zero-sequence current. This is the current shared equally by all three phases. A per-phase CT detects both phase-to-phase and ground faults by measuring the current flowing through each phase. Per-phase CT generate a signal proportional to the current flowing through their primary winding. This signal can be used to detect overcurrents, including those caused by ground faults. In a four-wire system with a neutral wire, the CT of a circuit breaker per phase can be used for ground fault protection. The neutral wire provides a return path of the ground fault current. The CT senses the current flowing through each phase and the neutral wire. By comparing the sum of the three-phase currents to the current flowing through the neutral wire, the relay can determine if a ground fault has occurred. If the sum of the phase currents exceeds the current in the neutral wire by a predetermined threshold, the relay trips the circuit breaker. This method of ground fault protection is effective because it detects unbalanced currents in the system caused by a fault to the ground. However, it is important to ensure that the circuit breaker is rated for the maximum fault current that can flow through the neutral wire. Zero-sequence CT are typically used in high-voltage systems where ground fault current magnitude can be high. Per-phase CT are commonly used in low-voltage distribution systems for ground fault protection. Ground fault protection is essential for electrical safety and preventing damage to equipment. Let's delve into the specifics of zero-sequence CT. These are designed to encircle all the phase conductors of a circuit, and sometimes the neutral conductor as well, depending on the system configuration. Their primary function is to detect any imbalance in the currents flowing through these conductors, which is a telltale sign of a ground fault. The principle behind the operation is based on Kirchhoff's current law, which states that the sum of currents entering a node, or a junction, must equal the sum of currents leaving that node. In a perfectly balanced three-phase system, the vector sum of the three-phase currents is zero. This means that under normal operating conditions, no current flows in the secondary winding of the zero-sequence CT. However, when a ground fault occurs, a portion of the current returns through the ground path, creating an imbalance in the phase currents. This imbalance is detected by the zero-sequence CT, which then produces a current in its secondary winding proportional to the zero-sequence current. This secondary current is then used to trip a circuit breaker or activate an alarm, isolating the faulted circuit and preventing further damage or hazards. The sensitivity of a zero-sequence CT is a critical parameter, as it determines the minimum ground fault current that the device can detect. This sensitivity is typically expressed in amps, and it is crucial to select a CT with the sensitivity appropriate for the specific application. For instance, in high-impedance grounded systems, the ground fault current is intentionally limited to a low value, so a highly sensitive zero-sequence CT is required. In contrast, in solidly grounded systems, the ground fault current can be much higher, so a less sensitive CT may be sufficient. Now let's turn our attention to per-phase CT. Unlike zero-sequence CT, which monitor the aggregate current flow, per-phase CT measure the current in each phase conductor individually. These CT are typically installed around each phase conductor at the circuit breaker or switchgear. Their primary purpose is to provide overcurrent protection, which includes protection against both phase-to-phase faults and ground faults. When a fault occurs, the current in one or more phases increases significantly. This increase in current is detected by the per-phase CT, which then sends a signal to a protective relay. The relay, in turn, trips the circuit breaker, isolating the faulted circuit. In the context of ground fault protection in a four-wire system, per-phase CT can be used in conjunction with a ground fault relay to detect ground faults. The relay monitors the current in each phase and the neutral conductor. Under normal operating conditions, the current in the neutral conductor is equal to the imbalance in the phase currents. However, when a ground fault occurs, a portion of the fault current returns through the neutral conductor, causing an increase in the neutral current. The ground fault relay detects this increase in neutral current and trips the circuit breaker. This method of ground fault protection is particularly effective in detecting high-impedance ground faults, which may not be readily detected by overcurrent protection alone. It is important to note that the effectiveness of ground fault protection in a 4-wire system depends on the proper coordination of the CT, the relay, and the circuit breaker. The CT must be sized correctly to accurately measure the fault current. The relay must be set to trip at a current level that is high enough to avoid nuisance tripping but low enough to provide adequate protection. And the circuit breaker must be rated to interrupt the maximum fault current that can occur in the system. Furthermore, the grounding system itself plays a crucial role in ground fault protection. The grounding system provides a low impedance path for the fault current to return to the source, which helps to ensure that the fault current is high enough to be detected by the protective devices. There are several different types of grounding systems, each with its own advantages and disadvantages. These include solidly grounded systems, impedance grounded systems, and ungrounded systems. The choice of grounding system depends on factors such as the voltage level of the system, the type of load being served, and the desired level of protection. In summary, zero-sequence CT and per-phase CT are both important components of ground fault protection systems. Zero-sequence CT are particularly well suited for detecting low-level ground faults in high-voltage systems, while per-phase CT are commonly used in low-voltage distribution systems for overcurrent and ground fault protection. In 4-wire systems, per-phase CT can be used in conjunction with a ground fault relay to provide effective ground fault protection. The choice of which type of CT to use depends on the specific application and the desired level of protection. It is also important to consider the coordination of the CT, the relay, the circuit breaker, and the grounding system to ensure that the ground fault protection system is effective and reliable. Now let's talk about current transformers in a bit more detail. Firstly, a current transformer, or CT, is a type of instrument transformer designed to provide current in its secondary which is proportional to the current flowing in its primary. CT are used for measurement of electric currents. They are also used to isolate measuring instruments from high voltages in the monitored circuit. A current transformer presents a negligible load to the primary circuit. The current transformer is based on the principle of electromagnetic induction. Secondly, a typical current transformer consists of a core made of laminated silicon steel. The primary winding may consist of a single turn or a few turns of heavy conductor, while the secondary winding consists of a large number of turns of fine wire. The primary winding is connected in series with the conductor carrying the current to be measured, while the secondary winding is connected to an ammeter or other measuring instrument. When current flows through the primary winding, it creates a magnetic field in the core, which induces a current in the secondary winding. The ratio of the primary current to the secondary current is known as the turns ratio of the CT. Thirdly, current transformers are classified according to their accuracy class, which indicates the maximum error in the secondary current as a percentage of the primary current. For metering applications, CT with high accuracy classes such as 0.2 or 0.5 are used. For protection applications, CT with lower accuracy classes such as 5% or 10% are acceptable. Current transformers are also classified according to their burden, which is the maximum impedance that can be connected to the secondary winding without exceeding the specified accuracy class. The burden is typically expressed in volt-amps. Fourthly, it is very important to never open circuit the secondary of a current transformer while the primary is energized. This is because the entire primary current becomes magnetizing current, which can cause a dangerously high voltage to develop across the secondary winding. This high voltage can damage the CT and pose a hazard to personnel. Therefore, the secondary of a CT should always be short-circuited or connected to a burden when the primary is energized. Fifthly, current transformers are used in a wide variety of applications, including power metering, protection, and control. They are used in substations, power plants, industrial facilities, and commercial buildings. They are used to measure current in high voltage and high current circuits. They are also used to provide signals to protective relays that trip circuit breakers in the event of a fault. Sixthly, when selecting a current transformer, It is important to consider the following factors: the primary current rating, the secondary current rating, the accuracy class, the burden, the insulation voltage, and the physical size and shape. The primary current rating should be equal to or greater than the maximum current that is expected to flow in the primary circuit. The secondary current rating is typically 5 amps or 1 amp. The accuracy class should be selected based on the application. The burden should be selected to match the impedance of the measuring instrument or relay that is connected to the secondary winding. The insulation voltage should be high enough to withstand the voltage in the primary circuit. The physical size and shape should be compatible with the installation location. Seventhly, current transformers are typically installed in switchgate circuit breakers and other electrical equipment. They are connected in series with the conductor carrying the current to be measured. The secondary winding is connected to an ammeter or other measuring instrument. The CT should be installed in accordance with the manufacturer's instructions and all applicable electrical codes. Eighthly, current transformers require periodic inspection and testing to ensure that they are operating properly. The insulation resistance should be checked to verify that the insulation is not degraded. The turns ratio should be checked to verify that the CT is accurately measuring the current. The burden should be checked to verify that it is within the specified limits. The connections should be checked to verify that they are tight and secure. Ninthly, current transformers are essential components of electrical power systems. They provide accurate measurement of electric currents and isolate measuring instruments from high voltages. They are used in a wide variety of applications for metering, protection, and control. Proper selection, installation, and maintenance of CT are essential to ensure the safe and reliable operation of electrical power systems. Now let's discuss ground fault protection in more detail. Ground fault protection is a critical aspect of electrical safety. Firstly, ground fault protection is designed to protect people and equipment from the hazards of ground faults. A ground fault occurs when current flows from a live conductor to ground, either through a person or through equipment. This can create a shock hazard and can also cause damage to equipment. Secondly, ground fault protection devices such as ground fault circuit interrupters or GFCIs and ground fault relays are designed to detect ground faults and quickly interrupt the flow of current. This helps to prevent electric shock and minimize damage to equipment. GFCIs are typically used in residential and commercial applications, while ground fault relays are typically used in industrial applications. Thirdly, ground fault circuit interrupters, or GFCIs, are designed to protect people from electric shock. They work by monitoring the current flowing in the hot and neutral conductors of a circuit. Under normal conditions, the current flowing in the hot conductor is equal to the current flowing in the neutral conductor. However, when a ground fault occurs, a portion of the current flows to ground, creating an imbalance between the hot and neutral currents. The GFCI detects this imbalance and quickly trips the circuit, interrupting the flow of current. Fourthly, ground fault relays are designed to protect equipment from damage caused by ground faults. They work by monitoring the current flowing in the grounding conductor of a circuit. Under normal conditions, very little current flows in the grounding conductor. However, when a ground fault occurs, a large amount of current flows in the grounding conductor. The ground fault relay detects this current and trips the circuit breaker, isolating the faulted circuit. Fifthly, ground fault protection is required by electrical codes in many applications. For example, the National Electrical Code, or NEC, requires GFCIs in bathrooms, kitchens, and other wet locations. It also requires ground fault protection for certain types of equipment, such as motors and transformers. Sixthly, when selecting ground fault protection devices, it is important to consider the following factors: the sensitivity, the trip time, and the voltage rating. The sensitivity is the minimum amount of ground fault current that the device can detect. The trip time is the amount of time it takes for the device to trip the circuit after a ground fault is detected. The voltage rating should be appropriate for the voltage of the circuit being protected. Seventhly, ground fault protection devices should be installed in accordance with the manufacturer's instructions and all applicable electrical codes. They should be tested periodically to ensure that they are operating properly. GFCIs can be tested by pressing the test button on the device. Ground fault relays should be tested by qualified personnel using appropriate test equipment. Eighthly, ground fault protection is an essential aspect of electrical safety. It helps to protect people and equipment from the hazards of ground faults. Proper selection, installation, and maintenance of ground fault protection devices are essential to ensure the safe and reliable operation of electrical systems. Ninthly, another key component of a comprehensive ground fault protection system is proper grounding. Grounding provides a low impedance path for fault current to return to the source, which helps to ensure that protective devices operate quickly and effectively. There are several different types of grounding systems, each with its own advantages and disadvantages. These include solidly grounded systems, impedance grounded systems, and ungrounded systems. Choice of grounding system depends on factors such as the voltage level of the system, the type of load being served, and the desired level of protection. Let's look at the implications for a full wire system. Firstly, in a four-wire system, which typically includes three-phase conductors and a neutral conductor, ground fault protection can be implemented using a combination of overcurrent protection and ground fault relays. The overcurrent protection is designed to protect against phase-to-phase faults and overload conditions, while the ground fault relays are specifically designed to detect ground faults. Secondly, the ground fault relays in a four-wire system typically monitor the current flowing in the neutral conductor. Under normal conditions, the current in the neutral conductor is relatively low, as it only carries the unbalanced current from the three phases. However, when a ground fault occurs, a significant amount of current flows in the neutral conductor, as the fault current returns to the source through the neutral path. Thirdly, the ground fault relay is set to trip when the current in the neutral conductor exceeds a predetermined threshold. This threshold is typically set low enough to detect ground faults, but high enough to avoid nuisance tripping due to normal unbalanced conditions. When the relay trips, it sends a signal to a circuit breaker, which opens and isolates the faulted circuit. Fourthly, the effectiveness of ground fault protection in a four-wire system depends on several factors, including the sensitivity of the ground fault relay, the coordination of the overcurrent protection devices, and the integrity of the grounding system. The ground fault relay must be sensitive enough to detect low-level ground faults, but it must also be immune to nuisance tripping. The overcurrent protection devices must be coordinated with the ground fault relay to ensure that they do not interfere with its operation. And the grounding system must provide a low impedance path for fault current to return to the source. Fifthly, in some four-wire systems, a zero-sequence CT may be used to detect ground faults. The zero-sequence CT encircles all four conductors, including the three-phase conductors and the neutral conductor. Under normal conditions, the sum of the currents flowing through the four conductors is zero. However, when a ground fault occurs, the sum of the currents is no longer zero, and a current flows in the secondary winding of the zero-sequence CT. This current is then used to trip a circuit breaker or activate an alarm. Sixthly, when designing ground fault protection for a four-wire system, it is important to consider the potential for harmonic currents in the neutral conductor. Harmonic currents are caused by nonlinear loads, such as electronic devices and switching power supplies. These currents can cause the neutral conductor to overheat and can also interfere with the operation of ground fault protection devices. Seventhly, to mitigate the effects of harmonic currents, it may be necessary to use a neutral conductor that is larger than required for the fundamental frequency current. It may also be necessary to use harmonic filters to reduce the amplitude of the harmonic currents. In addition, ground fault protection devices should be selected that are immune to the effects of harmonic currents. Eighthly, ground fault protection is an essential aspect of electrical safety in four-wire systems. It helps to protect people and equipment from the hazards of ground faults. Proper design, installation, and maintenance of ground fault protection systems are essential to ensure the safe and reliable operation of electrical systems. Now, let's talk about the importance of selectivity and coordination in ground fault protection. Firstly, selectivity, also known as coordination, is the process of ensuring that, in the event of a fault, only the protective device closest to the fault opens, minimizing the impact on the rest of the system. This is crucial for maintaining power continuity and avoiding unnecessary downtime. Secondly, in a coordinated system, protective devices are designed to trip in a specific sequence based on the magnitude and duration of the fault current. The device closest to the fault should trip first, followed by upstream devices if the fault is not cleared. This requires careful selection and setting of protective devices, taking into account their characteristics and the impedance of the circuit. Thirdly, there are several methods for achieving selectivity, including time current coordination, zone selective interlocking, and differential protection. Time current coordination involves setting the time current characteristics of protective devices so that they trip in a specific sequence. Zone selective interlocking involves communicating between protective devices to determine which device is closest to the fault. Differential protection involves comparing the current entering and leaving a zone to detect faults within that zone. Fourthly, time current coordination is the most common method for achieving selectivity. It involves plotting the time current characteristics of protective devices on a graph and adjusting their settings so that they trip in the desired sequence. The time current characteristic of a protective device is a curve that shows the amount of time it takes for the device to trip at different levels of fault current. Fifthly, when coordinating protective devices, it is important to consider the following factors: the fault current magnitude, the fault current duration, the time current characteristics of the protective devices, and the impedance of the circuit. The fault current magnitude is the amount of current that flows during a fault. The fault current duration is the amount of time that the fault current flows. The time current characteristics of the protective devices determine how quickly they will trip at different levels of fault current. The impedance of the circuit affects the magnitude of the fault current and the voltage drop during a fault. Sixthly, zone selective interlocking is a more advanced method for achieving selectivity. It involves communicating between protective devices to determine which device is closest to the fault. When a fault occurs, the protective devices closest to the fault send a signal to upstream devices, telling them to delay tripping. This allows the closest device to trip first, clearing the fault quickly and minimizing the impact on the rest of the system. Seventhly, differential protection is the most selective method for achieving selectivity. It involves comparing the current entering and leaving a zone to detect faults within that zone. If the current entering the zone is not equal to the current leaving the zone, then a fault is present within the zone. The differential relay then trips the circuit breakers that isolate the zone. Eighthly, selectivity and coordination are essential aspects of electrical system design. They help to ensure that in the event of a fault, only the protective device closest to the fault opens, minimizing the impact on the rest of the system. Proper selectivity and coordination require careful selection and setting of protective devices, taking into account their characteristics and the impedance of the circuit. Now, let's discuss the importance of regular testing and maintenance of ground fault protection systems. Firstly, regular testing and maintenance are essential to ensure that ground fault protection systems are operating properly and providing adequate protection. Ground fault protection devices such as GFCIs and ground fault relays can fail over time due to factors such as aging, corrosion, and exposure to harsh environments. Secondly, testing should be performed periodically in accordance with the manufacturer's recommendations and applicable standards. GFCIs should be tested monthly by pressing the test button. Ground fault relays should be tested annually by qualified personnel using appropriate test equipment. Thirdly, maintenance should include visual inspections, cleaning, and tightening of connections. Visual inspections should be performed regularly to check for signs of damage or corrosion. Connections should be tightened to ensure that they are secure and providing good electrical contact. Fourthly, testing and maintenance should be documented, including the date of the test, the results of the test, and any corrective actions taken. This documentation can be used to track the performance of the ground fault protection system and identify any potential problems. Fifthly, in addition to testing and maintenance, it is important to train personnel on the proper operation and maintenance of ground fault protection systems. Personnel should be trained to recognize the signs of a ground fault and to take appropriate action. They should also be trained on how to test and maintain ground fault protection devices. Sixthly, regular testing and maintenance of ground fault protection systems are essential to ensure the safety of personnel and the reliability of electrical systems. By performing regular testing and maintenance, potential problems can be identified and corrected before they lead to a ground fault. Seventhly, the specific testing and maintenance requirements for ground fault protection systems will vary depending on the type of equipment, the environment, and the applicable standards. It is important to consult the manufacturer's recommendations and applicable standards to determine the appropriate testing and maintenance procedures. Eighthly, in some cases, it may be necessary to replace ground fault protection devices that have failed or are nearing the end of their service life. Replacement should be performed by qualified personnel using appropriate replacement parts. Now, let's discuss some common troubleshooting tips for ground fault protection systems. Firstly, if a ground fault protection device is tripping frequently, it may be due to a ground fault in the circuit. The first step is to identify the source of the ground fault. This can be done by systematically disconnecting loads from the circuit until the tripping stops. Secondly, if a ground fault cannot be found, it may be due to a faulty ground fault protection device. The device can be tested using appropriate test equipment. If the device is faulty, it should be replaced. Thirdly, if a ground fault protection device is not tripping when a ground fault is present, it may be due to a number of factors, including a faulty device, a loose connection, or an incorrect setting. The first step is to check the device to ensure that it is properly installed and connected. Fourthly, if the device is properly installed and connected, it should be tested using appropriate test equipment. If the device is faulty, it should be replaced. Fifthly, if the device is not faulty, the settings should be checked to ensure that they are correct. The settings should be adjusted in accordance with the manufacturer's recommendations and applicable standards. Sixthly, if a ground fault protection system is causing nuisance tripping, it may be due to harmonic currents in the circuit. Harmonic currents can be caused by nonlinear loads such as electronic devices and switching power supplies. Seventhly, to mitigate the effects of harmonic currents, it may be necessary to use a neutral conductor that is larger than required for the fundamental frequency current. It may also be necessary to use harmonic filters to reduce the amplitude of the harmonic currents. In addition, ground fault protection devices should be selected that are immune to the effects of harmonic currents. Eighthly, troubleshooting ground fault protection systems requires a systematic approach and a thorough understanding of the system. It is important to consult the manufacturer's recommendations and applicable standards when troubleshooting ground fault protection systems. Now, let's consider the implications of ground fault protection for different types of equipment. Firstly, different types of equipment have different ground fault protection requirements. For example, motors require ground fault protection to prevent damage to the motor windings. Transformers require ground fault protection to prevent damage to the transformer core. Secondly, the type of ground fault protection required for a particular piece of equipment will depend on the voltage level, the current level, and the application. For example, high voltage equipment typically requires more sophisticated ground fault protection than low voltage equipment. Thirdly, ground fault protection for motors typically involves using a ground fault relay to monitor the current flowing in the motor grounding conductor. The ground fault relay is set to trip when the current exceeds a predetermined threshold. Fourthly, ground fault protection for transformers typically involves using a ground fault relay to monitor the current flowing in the transformer grounding conductor. The ground fault relay is set to trip when the current exceeds a predetermined threshold. Fifthly, in some cases, it may be necessary to use a combination of ground fault protection devices to provide adequate protection for equipment. For example, a motor may be protected by a ground fault relay and a ground fault circuit interrupter. Sixthly, when selecting ground fault protection for equipment, it is important to consider the manufacturer's recommendations and applicable standards. The manufacturer's recommendations will provide specific guidance on the type of ground fault protection required for the equipment. Applicable standards, such as the National Electrical Code, or NEC, will provide general requirements for ground fault protection. Seventhly, ground fault protection is an essential aspect of equipment safety. It helps to protect equipment from damage caused by ground faults. Proper selection, installation, and maintenance of ground fault protection devices are essential to ensure the safe and reliable operation of equipment. Eighthly, different types of equipment may also require different settings for the ground fault protection devices. The settings should be adjusted in accordance with the manufacturer's recommendations and applicable standards.